Well, it's very fortunate for me that I'm speaking right after the presentation that we just saw. We're going to build on the same discussion and the same concepts. So what IPMX stands for is Internet Protocol Media Experience. This is an AIMS term, and the actual technical specifications, in the previous presentation we saw that they reside on the VSF website as technical recommendations known as TR10. So we're going to look into describing IPMX equipment behaviors on SMPTE2110 networks, as well as other network profiles that add a little bit of flexibility. So again, borrowing a lot of the things that were done with AES23 and SMPTE2110, but bringing them into other utility cases. As a quick recap on SMPTE2110, this was primarily designed to help migrate SDI infrastructures to IP. What's in SMPTE2110, or what originally was developed in the VSF as TR03, are things such as the video format, which was YUV 422 10-bit, audio, as Andreas just covered, based on AES27, metadata, which is SDI ancillary, and synchronous signal, which is PTP. Andreas also covered the system-level additions that were introduced after SMPTE2110 was specified. These were things that were introduced to help simplify network configuration, registration, and connection management for 2110 media nodes. So there's, of course, the Network Media Open Specifications, or NMOS, that were developed by AMWA, and TR1001-1. So IPMX builds on this, and instead of only dealing with the SDI migration to IP, what about signal types that have different properties that need a little bit of different treatment? So IPMX really was intended to help better deal with this expanded universe of signals to keep a lot of the advantages of SMPTE2110 and expand them. So it's still the VSF, same group that developed TR3, which became SMPTE2110, that added these additional open specifications. They're known as TR10. And some of the things that were added were the video formats. In SMPTE2110, the mandatory video format is YUV 422 10-bit. In 2110, you can have 2110 products that support other color space formats as well, but in IPMX it's mandatory. IPMX requires you to support YUV 422, but also 444 and also RGB content. So this increases compatibility with equipment like PCs. If you're encoding a PC screen, for example, instead of a camera, this adds flexibility for that purpose. Audio remains based on AES67. Another thing that was added was the metadata. In order to deal with HDMI signals, HDMI is a consumer electronics type of connection. And you're all familiar with connecting an HDMI source to an HDMI display. There's some magic that happens, and they negotiate something with each other, and something appears on screen. If you're lucky, it's the exact correct resolution, and sometimes you're unlucky and you have to do something, but at least when you connect an HDMI source to an HDMI display, there's always something that appears on the screen. This type of information that is carried on the HDMI cable is EDID. So this type of info frame / EDID is added to the technical recommendations building on 2110. Another thing to deal with once we're dealing with other signal types, there's no HDCP in an SDI world, but in the Pro AV world, you might be connecting a source like a little Mac Mini or some type of media player that is outputting protected content. So the DCP LLC already had defined the carriage of protected content over IP, but one of the things that was missing was a mechanism to resolve the key exchange so that the source and the destination could exchange the keys in the same common way. So the VSF put a lot of work into this and developed something known as the HDCP key exchange protocol. What that allows is different product types from different brands all having the same way of exchanging keys with each other, so the transmission of HDCP content is made possible. Another really critical addition to IPMX is another method of building a synchronized network, and we're going to cover that specifically in this presentation. And then, of course, Andres already covered that NMOS was added after SMPTE 2110 was ratified. In IPMX, because it was already there, it just became mandatory. So IPMX devices, in order to call a device IPMX, NMOS is mandatory. This is to facilitate interoperability. So when we look at the picture, the expansion of IPMX is to deal with more things, but building on the strong capabilities of all of these standards. And there are some modes or profiles of IPMX that have direct media compatibility with SMPTE 2110. So for example, IPMX running uncompressed media, the media is compatible with SMPTE 2110-20 media. Or IPMX running constant bitrate compressed content, this is compatible with the SMPTE 2110-22 profile. So I don't know if you see the box that says SMPTE 2110. Although you can support multiple color spaces, as I mentioned earlier, what is popularly supported by most SMPTE 2110 products today is 422 10-bit, because the main mission originally was to just migrate SDI equipment to IP. With IPMX, RGB, YUV422 and YUV444 are all mandatory. Now, in addition to expanded color space support being mandatory, there are some additional profiles being added to serve the needs of Pro AV and IT with these standards. So additional mezzanine codecs, as well as high compression options such as HEVC and H.264 are possible with IPMX. So the type of network conditions that are possible with IPMX allow for expanded compression options, and we're going to cover that. So let's look at three main networking options that are all very valuable. They all have market utility. One is a PTP network using the 2110 networking methodology, or SMPTE 2059. This is still the market's best mechanism for synchronization at scale. If you're building an entire broadcast facility where you need synchronization throughout the facility, this is the market's best tool. But maybe you need a synchronized network, and the purpose of it is different. Maybe it's not to build an entire facility with synchronization. Maybe you need to synchronize something small, like 100 or 200 devices, or maybe you need a synchronized environment, but it's for a temporary event. Building a SMPTE 2110 network for an event that's going to last 10 days is maybe overkill. It might be a bit onerous. Maybe there's another option. IPMX introduces a second method of doing a PTP network that is a little bit easier to build and very useful for those types of situations. And of course, the majority of AV over IP products in the market, if we look at things like A-Speed devices or Crestron NVX or SDVOE or many of the other AV over IP protocols, almost all of them don't work with PTP at all. So most of the AV over IP market doesn't use PTP or synchronization at all. So IPMX also supports this wiring methodology, which has obviously a lot of utility in applications like control rooms and digital signage and sharing content to conference rooms and just general distribution of signals in a facility as think of it as an HDMI extension and switching replacement over IP, the way other AV over IP solutions work. So let's look at a couple of pictures to help illustrate what happens when you put IPMX equipment on these different types of networks. So in this particular picture, we see the conditions of a SMPTE 2110 network. So all of the sources are already synchronized. You see the SDI equipment is synchronized to the house sync, or if it's a native 2110 sender, it's synchronized to the PTP of the network. So the job of the 2110 equipment in this picture is to maintain that synchronization all throughout until the receiver point. Well, if you put an IPMX sender on this type of network, of course it will accept that synchronized source, and it will keep the synchronization like a 2110 sender. And an IPMX receiver is going to behave the same way as well. It will receive the content from that synchronized network and maintain the synchronization like the 2110 receiver. Now, let's look at another way to build a synchronized network, but a completely different methodology. In this case here, instead of building a synchronized network the 2110 way, we use ingredients in the IPMX technical specifications. The senders and the receivers and the NMOS controller allow PTP information to be coordinated between all of the senders and all of the receivers, whether the senders are converters from baseband to IP or native senders that are IPMX native senders. All of them can share timing information with each other through the NMOS controller. There's two major things that are different than the 2110 methodology. The network switch is not involved. It's not participating in the job of propagating the PTP information to all of the endpoints. The information on timing is synchronized between the endpoints themselves, and the switch doesn't care. The second difference is the level of PTP intensity is reduced. In SMPTE 2110, there's 8 sync requests per device per second and 8 replies from the switch to the device. That's 16 communications per device per second. If you have 100 devices on a network, that's 1,600 messages per second just to maintain sync. That's without having sent a bit of audio or video yet. So that's a little bit, again, onerous. That's what pushes the requirements for very specialized switching equipment. With IPMX, it was reduced in intensity. So the PTP in this second method that's available does 1/32nd reduction of intensity. So instead of 1 sync request per second per device, it's 1 sync request every 4 seconds per device. So instead of 1,600 messages per second for 100 devices, it becomes 50. So it's a big difference in network complexity on your networking equipment. So in this picture, what I'm illustrating is what it would look like in a practical application in Pro AV. So you could use a PTP signal generator on the network, and the default behavior of IPMX devices is that they're very good behaved devices on a network. They're PTP followers. So if they find a PTP on the network, they will lock to that PTP signal and all be followers to that PTP clock. In the example that I am illustrating here, I'm pretending that a manufacturer has implemented an option in their product to convert from being a follower, one of their endpoints, they turn it into a grandmaster. So this is an optional feature where a device itself can maybe be asked to become the orchestrator or the grandmaster of the network. So this is a possibility. So the grandmaster could be from an external source, or it could be one of the IPMX endpoints themselves if an option is exposed in the interface to turn that feature on. So this is very, very useful for rental and staging. This is useful for smaller, less complex synchronized networks. And of course, the most mass market case, just asynchronous signals that are not aware of the timing of the others. Basically, as soon as you start encoding, you transmit. There's no effort to align the senders with each other, and it's basically just a regular network with no PTP at all. So IPMX also works with this methodology. So you can go from the same IPMX senders in all three of these network examples that I provided. But the utility doesn't only end with the support for these three different options. There's actually utility combining some of these options. So I just re-shared the two different network types here. The one on top, the blue network, is your Pro AV network with all of the equipment just unaware of each other timing-wise, this asynchronous sources on a regular network. The bottom picture is a SMPTE 2110 network, and all of the SDI equipment that is being converted to 2110 is using the house sync. All of the native senders are locked to the PTP of the network. So that red network is a proper 2110 2059 network. So as you can see, the same IPMX equipment, provided it's IPMX equipment that supports 2110 media, the same equipment could be used on both network types. But beyond that, you would be able to connect the switch running your red network to some of your Pro AV switches running your blue network, and you would have portability of the content from the red network to the blue network. So if you look at the receivers on the upper right, the top right IPMX receivers can receive content from your studio equipment on your red network plus the asynchronous sources on your blue network. So this is portability from a 2110 network to a Pro AV network as well. Very, very useful. So there is significant customer interest in these types of mixed networks. Particularly larger organizations have studio equipment, but also have to deal with a significant amount of signal distribution throughout their facility. So this is what that might look like. You might have a red network or a PTP network operating all of your SMPTE 2110, quite often, uncompressed signals. And making this available on the broader network, there's a couple of things that can be done. Either the blue network could, be wired uncompressed and just have direct media portability, or you could put a media converter that converts from uncompressed to compressed and share a compressed version of the content to the blue network fairly easily. So there's already a lot of implementations that have been done to illustrate this. We did public demonstrations of these capabilities at Infocom in 2022. We did several other shows where we showed these types of networks, and there are some early stage networks being built this way at some Fortune companies, at some government organizations, at some large universities, and it's extremely popular. Another thing that is occurring is because of the portability of content from studio to Pro AV distribution, other types of products are popping out that are also quite useful. So there are gateways that are emerging that are allowing us to deal with either uncompressed to compressed conversions, or codec A to codec B conversions, or timing conversions. So if you want to introduce content the other way, let's say you want to take asynchronous sources from your network with no PTP and bring that into your studio network with PTP, there are some equipment vendors that are building that capability of adjusting for PTP those asynchronous sources. Some of the gateways that already exist are the ability to convert from HD base T to IPMX, or IPMX to HD base T. That's already something that you can find on the internet. Another one that was introduced a few weeks ago is NDI IPMX gateway, so that you can go from NDI to IPMX or IPMX to NDI. Putting IPMX in the middle allows you to do a great many things now. You can start with an HD base T source, go to an IPMX network, and output to an NDI player. Or you could start from a 2110 network with the output of a live production switcher and distribute that throughout your IPMX network as well. So again, the main point of IPMX is to keep everything that was so carefully built into AES23, into SMPTE 2110, in NMOS, and just add a few useful things that really open up the potential of those standards to a great many more applications. In a second session tomorrow, we're going to cover some of the specific things that were added to IPMX. So the RGB content, the info frames and EDID management, privacy, which is encryption, where organizations could load their own security keys into the devices for a cyber secure AV over IP deployment, and topics like this.